This is going to be a talk about special tetrahedra and special triangles. What's showing right now is about 140,000 tetrahedron centers, which I discussed a few months ago. But we're still waiting for this to start, so I'm going to give it another minute. But here's what a whole bunch of triangle centers look like. And if you go to, I think, I forget which mathematical games talk it is, but a few talks back I talked about tetrahedron centers, and this is an animation from generated from those 140,000 points. So I think we can start. Here we have episode 10, special triangles and tetrahedra. Mathematical Games was a column written by Martin Gardner for Scientific American. Martin Gardner wrote it for 25 years and developed a series of 15 books, which were highly influential for myself and many other mathematicians. So I'm trying to give these talks basically in a style similar to something Martin Gardner might do. We have more than 1,000 demonstrations involving triangles, and many of these deal with triangle centers, and a few deal with tetrahedron centers. But today I'm going to talk about some special triangles and special tetrahedra. And we'll start with the incenter, which is a intersection of the angle bisectors. This was something known, it's been known for 4,000 years, that if you bisect each angle of a triangle, they intersect at a point which is the center of a circle tangent to all three sides. So there's two triangles that you can get out of the special triangles. One is the cevians of the angle bisectors. That's the triangle in green. So when you draw a line through the incenter to the opposite side, a line through a particular point to an opposite side in a triangle is called a cevian. And the three cevians in green make what's called the incentral triangle. The contact triangle is the points where the circle is tangent to the triangle, where it makes contact. And that's the contact triangle in red. So this is something you can do with a triangle. You can also do it with a tetrahedron. So here we have a tetrahedron here. And if we do bisections of the dihedral angles, basically each of the edges here, each of the 6 edges makes a dihedral angle. If you bisect each angle of the tetrahedron, all 6 planes will intersect at the incenter point for the end-sphere, which is tangent to all 4 sides of the tetrahedron. And again, you can get two special tetrahedron based on that. If they go through the incenter, you take the cevians, where the vertex through the incenter intersects the opposite plane defined by the triangle, you get the incentral triangle. And if you look at the places where the sphere is tangent to the 4 sides, you get the contact tetrahedron for the original tetrahedron. So those are 2 special triangles or 2 special tetrahedrons, which have equivalents to each other in 2D and 3D geometry. And that's one thing I've been trying to do recently, is what things in 2D geometry also apply in 3D geometry. And not everything does, which we will see. the next thing we can talk about is the centroid, where the medians meet. And with that, you get the medial triangle is the Sevians of the centroid in red here. We've got the original triangle in gray. In red, we've got the medial triangle where the medians intersect. The anti-complementary triangle is the reverse. We have the original triangle in gray. In red is a triangle whose medial triangle is the original triangle. Median is basically a center of mass. And with a normal triangle, it's a midpoint, but for a triangle, it's the centroid. So if you connect up the centroids of each face in a tetrahedron, you also get a medial triangle. Each of these points is the centroid of the face. You can also do the anti-complementary tetrahedron, which is the reverse. Black is the original tetrahedron, and in red is a larger tetrahedron. And if you look at the centroids of each face, you get the original tetrahedron back. Another point is the circumcenter, and here it gets more complicated. In black, we construct the circumcenter. The perpendicular bisectors intersect at a point which is called the circumcenter, and it is the center of a circle which goes through all three vertices of the original triangle. In green, we have the medial lines, and the circummedial point is the green lines going through the centroid to the opposite arc of the circumcircle, and that makes the circummedial point, or the circummedial triangle. The tangential triangle is tangent to the vertex points of the circumcenter. So we have the original triangle here. We do tangency points, and the red lines are tangent lines at the vertices, and you get in red what's called the tangential triangle. Well, you can do that with the tetrahedron as well, but instead of perpendicular bisectors, you get midplanes. There are 6 midplanes which intersect at the center of the circumsphere. And the circummedial points are the intersections of the sphere with the vertices going through the centroid point. So in black, we have the original tetrahedron. In red, we've got the circummedial tetrahedron. The tangential tetrahedron is tangent to the vertex points on the circumsphere. So in black, we've got the original tetrahedron. In red, we've got the we've got the tangential tetrahedron. So all of these are inside of a new function on the WFR site, Wolfram Function Repository site, and it's called subtetrahedron. There's also another function there called subtriangle, which we've had for a while. And those two programs will generate many of these special triangles and special tetrahedron. So here's where 2D and 3D break down. The fourth famous triangle center is the orthocenter where the altitudes intersect. If we basically drop altitudes to the opposite sides from each vertex, we get the feet, and they intersect at the orthocenter. There's no corresponding center in 3D. Sometimes it works in what's called an orthocentric tetrahedron, but it doesn't always work. When they do intersect, it's the same as the Mange point, which we'll cover on the next slide. Most of the time, though, they do not intersect. However, we can still connect up the feet where these altitudes meet the opposite side, and the connection of the altitude points gives the altitude tetrahedron. We can also do the Circummange tetrahedron where the Mange point intersects, going through the vertices through the Mange point to the opposite edge for the circumsphere. That's one I tossed in. So the Mange point, if you connect up a midpoint of one edge so that it's perpendicular, but through the opposite edge, you get what's called the midplane. And Gaspar Monge noticed that all 6 of these planes intersected at what's called the Mange point in any tetrahedron. And this is very similar to the orthocenter of a triangle. So this is considered the 4th important tetrahedron center, the Mange point. If you reflect a tetrahedron by the Mange point, you get this, or reflect by the centroid, you get this attractive figure. I'm not sure what this is supposed to be called, but I'm calling it the negative tetrahedron in the function. So if we have this property with opposing edges of a tetrahedron, so that the sum of squares for each opposing edge is the same, then we have the property that all 4 of the altitudes intersect. And that's called the an orthocentric tetrahedron. So it's a special type of tetrahedron. Also, if you join up the midpoints of each edge, what's called the bimedians, if the bimedians have the same length, then you also get the property that the tetrahedron is orthocentric. However, if either of those 2 properties is false, where the bimedians are not the same, or if the sum of the squares of opposite edge lengths is not the same, then it's not orthocentric, and the altitudes will not intersect. Let's see, the next important point in triangles is called the center of the 9-point circle. So if you have the feet where the altitudes are, and the midpoints, and the midpoints of the vertices to where the altitudes intersect. So in yellow, we've got the midpoints to the orthocenter. In green, we have the altitudes. And in red, we have the medial triangle. So it's the orthic triangle, the medial triangle, and the Euler triangle. Euler was the one who made this yellow triangle famous. Those 9 points are what's on the 9-point circle. And it's tangent to the 3 X circles. There's something similar with tetrahedra. the medial points of each triangle, the 1/3 distance points between the Mange point and vertices. So we'll call those the Euler points. So this is the Euler tetrahedron, the medial tetrahedron, and the altitude tetrahedron. We get these 12 points, which are also on a sphere. And there's the 12-point sphere of a tetrahedron. And here's it showing in a different way as 3 tetrahedra, all having the same circumsphere. This sphere is not tangent to the 4 X-spheres. And we can check that the Euler tetrahedron, the Euler projected tetrahedron, and the medial tetrahedron all have the same. These are the 4 tetrahedron, but these are the 3 tetrahedron, but they all lead to the same sphere. Oh, what is my comment here? The sphere tangent to the X sphere is close to the 12-point sphere. I call it I'm going to call it the Feuerbach sphere for now. Feuerbach was the one who proved that the 9-point circle and the in circle and the 9-point circle have a single tangency point, which is called the Feuerbach point. Since there is no name for this sphere, I'm just calling this the Feuerbach sphere for now, which is tangent to the 4 X-spheres. So there's extra points that we could make out of this, but I haven't done that yet. But the tangency points in the subtetrahedron function, I call that the Feuerbach tetrahedron for now, until I come up with a better name for it. And these are in the center there, that's the sphere tangent to all the X-spheres. The Submedian point, we have the centroid here. We can do the angle bisectors, and if we reflect the lines, we get what's called the Submedian point, the reflections of the medians in the angle bisectors. That point minimizes the sum of distances squared, and we can check that. The reflections of the median planes and the dihedral angle bisectors also works. So here's the same thing in the tetrahedron. G is the centroid, K is the Submedian point, and we can get the Stevians of the Submedian point to get the submedial tetrahedron. X circles and X spheres lead to a lot. So here we have a triangle in the middle here. That's the original triangle. We can make the X circles, and if we connect up the points, we get the X central triangle. If we look at the tangency points, we get the X touch triangle in green. We can do the same thing with 3D, but it's a little bit more complicated. Here we have the X-spheres function generating the 3 X-spheres of the tetrahedron in red, and in gray is the X central tetrahedron, and in blue is the X touch tetrahedron. And these are all part of the subroutine function on the Wolfram function repository. One I wasn't able to get quite working yet because the code is hacky. Here's somewhat hacky code for picking out the planes tangent to the each of these planes is tangent to the 3 of the spheres. So, however, the original tetrahedron also has planes that are tangent to 3 spheres. It's actually tangent to 4 spheres, but when we're generating solutions, for example, there are 2 planes tangent to 3 of these spheres, and there's probably more planes. It would be nice to have a full set of solutions, but for these particular planes on the outside, the 4 planes intersect to get the X-tangent tetrahedron. And while I was making this talk, I happened to notice that if you connect up the points of the X-tangent tetrahedron and the original tetrahedron, they all meet at a point right over here. You can barely see it, but at the center there, we get a new tetrahedron center. Now, I was surprised to see this because with triangles, if you connect up 3 lines that are related to each other, there's a pretty good chance that those 3 lines will intersect at a point. And there's thousands of triangle centers where people have noticed, well, there's these 3 lines correspond to each other, and when we connect up the 3 lines, they all meet at a point. That happens all the time. But with tetrahedra, that almost never happens. There's like 8 occurrences where that's known to happen. Well, this seems to be a new one. The concurrence point for the X-tangents tetrahedra and the original tetrahedra seems to produce a new point, and we can check that with a different tetrahedron. And here that is here. I've tried it with some others, and it always seems to work with tetrahedra of any type. When you make the X-tangents tetrahedra and connect up the corresponding points with the original tetrahedron, they meet at a new point. But I haven't figured out what that point is yet, or why this works. And I haven't proved it yet either. So that's a new tetrahedron center that was found last night. So now I'm going to switch over to special triangles and special tetrahedra of various sorts. So here we have a hexagon. Just take vertices 1, 2, 4, or any 2 neighboring points, and skip over 1 to get a 3rd point. Well, it turns out if you reflect each vertex on the opposite edge, for example, in green here, you get this point here. From this point, when you reflect on this edge, you get this point here. And when you reflect this edge on that edge, you get this point here. Well, it turns out you get another triangle, which is similar to the original triangle, but twice its original size. Exactly twice the area. And it turns out that there are intersection points from the diagonals which lead to all but one of the points of a new heptagon, which is twice the area of the original heptagon. And it turns out that this is the one of only 2 triangles that have this problem, where the reflection triangle, this process of flipping all the vertices on the edge, that gives what's called the reflection triangle. And there's only one other triangle that has a similar reflection triangle. That's this right here. And these have a size ratio of 2 over the golden ratio. And an unsolved question is there a tetrahedron that has a similar reflection tetrahedron? I only spent about an hour trying to solve this, and this is the best I got. This is 0.009 away from being similar to each other. We've got an original tetrahedron over here, and we've got the reflected tetrahedron over here, where we reflect each vertex by its opposite triangle, the plane of the opposite triangle. And when you do those reflections, you get a tetrahedron, which is very similar to the original. So this is an unsolved question. Is there a tetrahedron with a similar reflection tetrahedron? Another set of special tetrahedra is ones which will fill space. And for 2 cases, we get something weird called an orthoscheme. So here is a tetrahedron divided into 8 parts, which are all similar to the original tetrahedron, all 1/8 size of the original. So here's one way of doing it, and that's ortho 1. And here's a second way of doing it. This is ortho 2. So these are the 2 orthoschemes that I know about. There's only 5 tetrahedra that fill space. Here's the first one. We can divide this skew prism up into, 3 parts to get what's called Somerville 1, Baumgartner T, or Hill I 160. Here's another Somerville 2. This is a way of dividing up a cuboid into, 6 similar parts. Here's a third solution, a way of dividing up a cube into, 12 parts, I think. And another prism dissection. Here is 12 tetrahedra making up a prism which will tile space. And here's the last one, generating another prism which will tile space. This is the weirdest of the space-filling tetrahedra. So these are all special tetrahedra. There's also what came to be known as the Conway tetrahedra. So here's something else first. We have 3 integer vertices. And for Zach, you can make a space-filling fractal out of the orthoschemes. So here we have 4 points that are integer coordinates, and the Euclidean distances are 6, 7, 8, 9, 10, 11. So that's kind of a special tetrahedron. I'd like to find more of those, because when you have, and I used this several times in this talk, when the edge lengths are nice, sometimes the generated special tetrahedra and special tetrahedron centers also have nice coordinates, but not always. There's always ways of making things more complicated, but usually if the edge lengths and things are on integer coordinates, usually things work out more neatly. And another thing, in addition to rational edge lengths, is whether the dihedral angles are rational in terms of pi. And John Conway wondered what was the full set of tetrahedron where all of the dihedral angles were fractions, rational fractions of pi. And it turns out that a recently published paper, this paper here, Space Vectors Forming Rational Angles, 2020, did a complete compilation of all of the tetrahedra, and it turns out that if you use an icosahedron or a 3x3 lattice, you can get all but 3 of the tetrahedra that have these properties where all the dihedral angles are nice. And there's 3 more that can be derived from this tetrahedron. These are the points that generate it, and the dihedral angles are right here. If we go to this community page, and I'll be posting this on the link. You'll be able to see all the links. This gives the solving method for finding this particular tetrahedron. Let's see. Solid angles. Well, I might as well read this. During an eclipse, the moon and sun seem to have roughly the same size viewed from Earth. That's because the field of view is the same, even though they're very different distances apart. And that field of view is called the solid angle. The unit sphere around the observer has a solid angle of 4 pi steradians. And that's the same as the surface area of a sphere. And for a tetrahedron, the solid angle is defined as what an observer at a vertex sees when looking at the opposite triangle. And one thing I thought was that the smallest solid angle corresponded to the smallest of the 4 triangles, but that doesn't seem to be the case. There are weird tetrahedra that violate that. When 2 planes intersect, the angle is called the dihedral angle. So here we've got a tetrahedron. For this special tetrahedron, the solid angles are 1/12, 1/6, 1/12, and 1/2 all times pi. And the dihedral angles are 1/2, 1/3, 1/2, 1/3, 1/2, 1/4. So this is a Conway tetrahedron. And there's a property of tetrahedron. First, for a circle, if you add up the 3 angles of a triangle, you get 2 pi. If you multiply by 2, so twice the sum of the angles of a triangle is 2 pi, the full circle. Twice the sum of the dihedral angles minus the solid angles is 4 pi, the full sphere. That's the corresponding angle sum formula for a tetrahedron. Twice the dihedral angles minus the solid angles is 4 pi. And we can look at various special tetrahedra. Here's another one. So this is also a Conway tetrahedron. And also this. So I'm going to try to compile a complete list of all the 59 Conway tetrahedron for a database. That's on my to-do list. Let's see here. Here's another special tetrahedron. We have these values here are powers of a given root. So for this one, I've picked the root, which is the square root of the Fibonacci constant, 1.39 or 1.38837 and so on. So the Fibonacci constant to the power of 0 gives this edge length, power of 1 gives this edge length, the power of 2 gives this edge length, and the power of 3 gives this edge length. So this is what's called a similarohedron, because all 4 of these triangles are similar. The 2 smaller triangles with the 0 edge, if you multiply each one of them by the root, you basically pump up one for each. So instead of 0, 1, 2, you get 1, 2, 3. So this is a special tetrahedron built up of similar triangles, and you can change the root, and you get different tetrahedra. But this particular one, if you put it on the ground and you roll it, there's only 12 orientations that you get, and it makes this hexagon. So a Fibonacci tetrahedron, if you roll it, will only have 6 orientations if rolled on a plane. And this was not known, apparently, that there were tetrahedra with this sort of property. Let's see, there are currently 53,000 triangle centers, and here's the first 6 of them, and we covered them earlier. Some years ago, I decided to see what these triangle centers look like, and this is an animation of a triangle warping, and you basically see how the triangles how the triangle centers move around. So this is just a few hundred triangle centers. And what I started with at the start, I think, somewhere here. Here's a whole bunch of tetrahedron centers for a given tetrahedron. It's harder to see what's going on when you're in 3D. So basically I had to stick to one tetrahedron to generate these 140,000 different tetrahedron centers. And I described how I got all those in the talk that got mentioned earlier. The Euler line goes through the Circumcenter, Centroid, 9-point center, and Orthocenter. And the isogonal conjugate of the Euler line is the Jerabek hyperbola. These have these positions in relationship to each other, and you can basically skew this line. This point is to here is half the distance from this point to here. It's always this -2, 1, -2, 0, 1, 4 relationship. We can do the same thing in tetrahedra. We get the Euler line. We also get a Jerabek hyperbola. But the Incenter and Submedian are off the Euler line, but they're on the hyperbola. However, the positions are slightly different. Instead of what they were before, now it's -2, 0, 2/3, 2. And we use the Mange point instead of the orthocenter. I mentioned Stevians earlier. You have a given point and it goes to the opposite edges. I plan to make a Stevians function that'll work for either triangle or tetrahedra. Here's another new center I found a little while ago. Opposing edges If you define them like this, you get a constant. It's the same for each pair of edges in a tetrahedron, and it's called the dihedral constant. And you can take another point so that if you connect up the triangles with that point, each of the four triangles with that point has a dihedral constant, which is the same for all four faces. And that's called the dihedral constant center. And it turns out this point does exist. That's another point I plan to add to the database I'm working on. And here's the theorem in action. As you adjust the tetrahedron, the dihedral constant of the tetrahedron is always the same. Another point which is shown to exist in the tetrahedron is parallelions point. And basically, we're going through a single point so that the areas of the four triangles is the same. And each triangle is parallel to the given face and going through the equal parallelions point. There's not many tetrahedron centers known, so we've been trying to build up a little database for when they work. And I've got a demonstration that has many of these tetrahedron centers, and I need to update that one to include many of these new points and to update the code to use WFRs that we've been putting together. We also have a isogonal conjugate resource function. I'm going to be adding a isotomic conjugate resource function soon. And they work with both a tetrahedron and a triangle. It turns out there are 4 tetrahedral points and 8 self-conjugate points. And this is a diagram of how they connect together. One thing I need to check is whether that special point from the x-tangents tetrahedron, whether that given point has anything to do with any of these self-conjugate points. And I need to describe everything in areal or barycentric coordinates for all of these centers, important centers that have been found. This is kind of a discussion for how barycentric coordinates work. And the barycentric coordinates can also be done in a tetrahedron. For example, you've got this given tetrahedron here and a given point. The areas of the 4 generated tetrahedra compared to each other is basically the areal or barycentric coordinate. Either the volumes, have the four volumes, assuming that the original tetrahedron have all volume 1. These would be the volumes of the 4 tetrahedra generated by that point. And once you have areal coordinates, you can do fairly amazing things like here are generators for areal coordinates. And when you connect them up, you get 149 points and 241 lines of 5 points. And trilinear coordinates are the same as areal, but they're divided by the opposite edge, I believe. And in a tetrahedron, they're divided by the opposite faces. And there's some odd things with trilinear. So So that's a project I'm working on, is getting all of these defined in areal and trilinear coordinates for each point. Here's what they look like as triangle functions. The centroid is, if you have the triangle with sides A, B, and C, the centroid has trilinear coordinates of 1 over A, 1 over B, 1 over C. The centroid is well defined for a tetrahedron, but the formulas are much more complicated for a tetrahedron. So I need to basically get all these into Mathematica. That's a project that I'm working on. And I hope to have, within a few weeks, I'll hope to have this animation that I've shown a few times as a much more dynamic object. And that's what I had prepared. We can get into the unsolved questions, which is basically everything. For example, what is the tetrahedral formula for the Fermat point? We've generated many special tetrahedra, but there's various that are not listed yet. It'd be nice to have more special tetrahedra added. If anybody has code for any, I'd be glad to add that to the subtetrahedron function. And if there are special lines or parabolas and things like that, those would also be good to have as a function. I may as well show the subtriangles function, and also special triangles. If there's other special triangles that could be added to this, let me know and we can try to add them to this. So I plan to make a database of the Conway tetrahedra, plan to expand subtetrahedron. I'm going to be putting together functions, isotopic conjugates, Sevians, plane line intersection, and some other support programs. If anyone has anything that works in both 2 dimensions and 3 dimensions for triangles and tetrahedra that we don't have yet, let me know about it, and I'll try to come up with a function for it. Here's my address, and I will be glad to take any questions that people have. Go ahead and post in YouTube or wherever you're listening from, and I'll be glad to try to answer them. Does anyone have any questions? For space filling, I'm trying to come up with things similar to, let's see here. And I talked about this in a previous talk where, so here's a space filling triangle, which was unknown. Shattering the plane is what you'd want to look for. And here are 5 space filling triangles that were unknown. Each is generated by similar copies of itself. One is based on 2, one is based on the golden ratio, one is based on the super golden ratio, one is based on the chi constant, and one is based on the plastic constant. And all 4 of these values have the property that there are sums of infinite series of themselves in reciprocal. 2 is the sum of 1 plus 1/2 plus 1/4 plus 1/8 and so on. The golden ratio is the sum of the same sort of thing, but skipping the first power. The super golden ratio skips the first 2 powers, the chi constant skips the first 3, and the plastic constant skips the first 4, and you get these polynomials and values. And it turns out that all 5 of these lead to special fractals. I found all of these by asking the question, is there a way of surrounding a point with similar triangles? And I wrote a program, wheel powers, it's on the demonstration problem, triangle wheels. And it wasn't too hard to solve. And when I found this, I figured I could extend that to come up with a similar triangle solution, and then it worked. And there it is there. And that's what I did with all of these. There was a weird way the triangles interfaced, and I could extend them to work out. So the question is there a way of surrounding a point with similar tetrahedra? And that's an unsolved question. I'm not sure how to solve it, but it shouldn't be too hard to solve. And if there are solutions to that where similar tetrahedra will can surround an angle, then there's probably ways of generating some really weird new fractals that have never been seen before. So that hopefully answers Zach's question. You'll probably want to look at Rousey fractals to see what's known about these self-sum things. Rousey fractals, Rauzy, have lots of weird properties, and they're basically generated by simple matrices. So it's not too difficult to come up with new Rousey fractals. However, most of the interesting ones tend to go to those 5 constants. Any other questions? All right. Let me see if we can find. All right. Many thanks for attending my talk.